Alright, this is my second attempt at this video because the first time my audio wasn't working. So actually, let me check that. Okay, it looks like audio is being captured. That's good. Alright, this is my second attempt. I've got a couple more backwards induction problems, examples for you to think about. So the first one here is the penny game with a twist. Alright, so you take out 1 to 6 every round starting at 50. However, you can't end your turn on a multiple of 5 or you automatically lose. And you want to take out the last piece. So as we talked before, right, in this case, the min plus the max equals 7, right? So the person moving second, so the second mover at multiple at 7x or whatever wins. So you want to leave 7x after you play. That's normally what would happen, right? So the first player takes out 1, then wins, right? Does that make sense to everybody? Okay. First player, that's what would happen if it wasn't this multiple of 5s thing. That creates a little bit of a problem. So let's look at how that plays out as we go backwards. So this is all old stuff, as if there isn't the special conditions. But what happens? So we still want to get to 7. If you get to 7, if you remove to 7, you win. So after your move, you want 7. Then you want 14, still good, right? Then you want 21, still works, right? Then you want 28, still good. And then you want 35. Here's a problem, right? If you end it at 35, you lose. So you actually don't want 35. So what can we do instead? Well, what if you leave 36? Now, your opponent, normally I'd say, well, I mean, your opponent can take out 1 and then they win, right? And because then they're a multiple of 7. But in this case, they can't. At 36, your opponent can't take out 1. They have to take out between 2 and 6, and then you can take out between 1 and 6, right? So you can force 8 at that point. You don't just have to force 7. You can force 8. And to get to 36, you can force it from 43 and 50, right? So basically, by adding this multiple of 5 things, we've gone from a first player wins to now the second player wins, as long as they take it out to 43, 36, 28, 21, 14, and 7 after each of their turns. Okay? Alright, moving on here. Let's look at the pirate game. We've got 11 pirates, only 4 gold coins. So basically we're in a situation where there is more than twice as many pirates as there are gold coins. Let's see what happens. So right, we got in the last round, there's only 1 pirate left. This is the number of pirates left, right? This guy would get it all. And in the previous round, therefore, we would go 4 and 0. This is because the second to last pirate wins the tiebreaker. So they take 4, and the last guy gets 0. In the third to last round, right, this guy, the third player knows he can't persuade the second player, or the second pirate. Third pirate can't persuade the second pirate to vote for him, so there's no reason to give him any. But he knows that in the next round, the last pirate will get nothing. So if he gives him 1, we get 0, and 3. So this would pass, right? Because both this pirate, the third pirate, and the last pirate would vote for it. And we can sort of go back in the same pattern. Well, the person before that, they can persuade this person to vote the second pirate, or second to last pirate, because otherwise they're going to get 0. So we go 1, 0, 0, 3. And again, this works because this person and this person vote for it. So let me highlight the people who are voting for it. And the reason these people are voting for it is because it's better. They're going to get more than they would in the next round. Okay. So we keep going. Next person has to make a decision. He needs to get the fifth pirate needs to get 2 other pirates to vote with them. So, easiest way to get that is to go for these 2, because they were going to get nothing, right? And we can keep on going backwards. And I hope you're seeing the pattern here now. So we go 1, 1, 2, and then we get 1, 1, 1, 1, and we get 1, 1, 1, 1. Actually, let me highlight all that as red. And then we get all these like that. Into 1 there. That's got to be red. Okay. So again, red is people who voted for it, and that's got to be black. I have some wrong ones here. Alright, so how do we get to here? Hopefully this makes sense up to this point. This is sort of the pattern we get. So what happens here? The 9th person still needs to get 4 other people, the third pirate, the pirate 9, who's the 3rd strongest, still needs to get 4 other people to vote with them. So it's a 5-4 vote. And so the best way to do that is to give 1 to these 4 people. Again, can't give it to any of the people who would already get 1 the next round, because remember, pirates slightly prefer the next person to die, right? But unfortunately, that means they can't give any to themselves. Now, they might be willing to do that, because if they don't do that, they die, and dying is obviously bad, right? So they'll take the loss, as much of a loss as it is, but they will still vote for it. And then these people will not vote for it. Pirate 10 does basically the same thing. They give themselves 0 because they want to survive, and they persuade the people who have who are going to get 0 the next round to vote for it. So they get these votes. And these people get nothing. What about the first pirate? Most powerful of the 11 pirates. They need to get 6 votes. Obviously, they're going to vote for it themselves, and they don't want to die, so they'll give themselves 0, and they'll vote for that. Sure. They need to get 5 other votes, and they only have 4 coins. Well, they could give 1 here, 1 here, 1 here, 1 here. Those people would all vote for it. But that's only 4 votes. There's no one else they can give. There's no one they can give, and there's no one else they can give a 0 to that will vote for it. In fact, there's no one they can give a 0 to, because everyone else who's going to get a 0 next round, okay, would prefer the first pirate to die. So there's actually no possible way for Pirate 11 to survive. Once you get past twice the number of gold coins plus 2, so if the number of pirates is greater than 2 times the gold plus 2, captain dies, and they keep dying until we get down to that 2 gold plus 2. So 10, the captain survives, right? This is voted for. So this is sort of the Nash equilibrium outcome of this circumstance. It is the final one where people actually vote for it. Okay? All right. One more. We're going to play another new game here. This is one we haven't played before. It's 4 players. Each player chooses a distribution of 10 points and distributes them. Says, I'm going to get this many, you get 1, you get 2, and the other players, and you vote on it. You need at least 3 votes to pass. If the vote fails, then the next person proposes, but 1 point is removed from the pool. So if player A proposes 10 and no one votes for it, then the next player has 9 to distribute. Okay? Players want more points, but if all else is equal, they'd prefer not to have points taken out of the pool. So in other words, if I'm going to get 0 either way, or I'm going to get 2 either way, it doesn't matter, I would prefer you get 7 than you get 6. Does that sort of make sense? So we're sort of we want generally, we're happy when other people get more. We're happy if we get more, but we're happy if other people get more. So first thing we need to do is we need to figure out who's going first in each of these rounds. So who's proposing. So here it's this guy, then the second, the ninth, and there's 9 left. It's this person. So we're just marking, right? It goes like this. These are the people proposing. Oops, not that one. These are the people proposing. Okay. So, second player, when there's 1 left, what are they going to propose? Well, they're going to keep it, right? There's no reason not to. They're going to keep it. They're going to give themselves 1. Everyone else is going to get 0. And they're all red right now because that everyone's going to vote for it, right? You might as well have other people be happy. That's better. So what does the player in front of them do? They say, hey, I need 3 votes. My own, and I need 2 others. Who can I persuade the cheapest? Well, right, a tie is better. Like, we appreciate, if I'm going to get 0 either way, I actually will vote for it. So these 2 people I can vote will vote for it with 0. And I don't need this person, so they will not vote for it. But then I get to keep 2. So thinking back to that, what's this player going to do? They again know they only need to get 2 votes. So maybe they get third player still going to vote for it because they get 0 no matter what. And this person knows that next round they're going to get 0, and they'd rather there be more points available than fewer. So they get this 1 or 3, sorry, here. And this player obviously doesn't vote for it because next round they would get 2. And the same logic holds the whole way through, that no matter what, if you give yourself all the points, you can get 2 other people to vote for you. Right, again, we're thinking like, again, if it's in the row above, if it's the same or bigger, you vote for it. Right? So even though that seems to like thing, like how would you possibly get 10 by giving no one else anything? The reason is because deep down we know that eventually we're going to get to this point. And because we're, in this case, everyone is happy with other people getting it better than them getting. It's happy that if the other people get more, if they're going to get the same amount, which is not really always true. Like right in life, that's somewhat unlikely outcome, but that's how it would work out. All right, that's it for me.